Okay, for the last few minutes, I've got one more thing to show you here that will help you understand this a little better. And that is, I have bad news, which is that, let's see, I was overlooked for the Nobel Prize this year. I didn't think I was going to be here today. I think when I sent the check in, I forgot to convert it to kronas or something. But the winners were Arthur Ashkin, Gerard Mural, and Donna Strickland. A big optics person. I think she's something in the Optical Society of America at the moment. And she's the third woman to win a Nobel Prize in physics ever, which is pretty good. I'd be a little intimidated by being in the company of Mary Curie and Mrs. Geppert. I forgot her last name. It's hard to say. But it's very exciting. And the first one, though, so the second two, Strickland and Morrow. Oh, and also Strickland is an associate professor. She's not even full professor yet. So I have a feeling that's going to get turned over. It may be the most rapid P&T committee decision ever. I don't know. But Arthur Ashkin did something exactly relevant today, something with momentum, right? Trapping particles. If you read, you can read the scientific background of a Nobel Prize win, and it's really sort of scientific American level. Like, you can read it and understand it. And it's also really, the point of it is it's justifying all the people who didn't win, right? So if you see anybody cited in one of these documents, they're like really pissed off, because that's the point of the document. It's just to educate the public. But this is a figure from the document, and it's about how you can use light to trap a particle. Somebody's... Okay, we'll get to that in a minute. It's how you use light to trap a particle. So you can, if you just shine a laser beam on a little dielectric particle that causes refraction, the particle stays inside the beam. We're going to do every aspect of this before the end of the year. We're going to do geometrical optics and all kinds of stuff. So today I'll just describe a little of that, but I want to show you why the particle is trapped in the beam. It's exactly what we've talked about today. It's impulse. It's literally impulse. So let's say here's the particle, right? And a laser beam is not uniform in space. If it was, it'd be really big, right? A laser beam is this teeny little beam. For a laser pointer is small. So if you were to look at like how bright is it versus position, it's like a curve like this, right? It's like, oh, it's like that. Right? So say your particle and your beam are about the same size, whatever. So now light, you have this ray tracing, maybe you've seen before. So you could bring in light like this, and if the particle's in the middle of the beam, you have the same amount of light here, and you have the same amount of light here, right? Like that. And then light, when it goes into a dielectric like glass, it falls to the normal. Like that, and then it is away from the normal like that. So you get something, I haven't drawn it perfect, but something like that. Okay, the light's going to come in. Now, a long time ago, there was an argument of whether light is a particle or a wave. Well, it's a particle. Newton won, light's a particle. It's actually a bunch of little photons coming along like that. And those little photons turn like that. What does that mean? They had to have had a change in momentum, because they actually do have momentum. Right? Light carries momentum with it. That's why it can push things around. One question is, do we still have pledge problems due Monday? No, we've never had pledge problem. We've only had one pledge problem so far. So there's no pledge problem. The homework that was due, maybe the calendar says there's one. There's one. The homework that was due Wednesday, I'm moving to Friday. Okay, so what we got to think about here is, we're going to call this A on the left and B on the right, and we'll say it has an initial momentum, P, A initial, and then here's the final momentum, P, A final. Because all the photons that go in come out. They just get bent by the particle. And PB looks like this, a momentum, B initial, PB, a momentum, B final. So let's think about what impulse it would take to create that, right? JA equals delta PA. How much did this momentum change? Final minus initial. So we draw the final vector like that, and then we add, A went the other way. A goes this way, right? And then we add the negative of the initial vector like this, like that. So A had an impulse that way. There's JA, there's delta PA, or whichever one you want to call it. So the photon got pushed that way. And then we do B equals delta P, B, and it looks like this. So delta PB is that way. Final, initial, delta P or JB. So we say the photons felt a kick. The photons felt a kick like this. If you vector add those, the lateral parts cancel and it pulls back a little bit. Right? So that's total J on the photons. But if every action there's an opposite and equal reaction, what do you get? Oh, the bead was pushed forward a little bit. Okay, so what? Who cares? I know. That was the kind of question you're not supposed to answer. Now, let's put it over here. What if the bead sort of drifts to the side and starts to try to leave the beam? Now it's bright here. Okay, now you can see where we're headed, and it's really weak here. Right? A lot of photons here, just a few photons there. A lot of photons giving me this kick, and just a few giving me this kick. Okay, so which one gave which kick? The strong one was B. We get a strong kick this way on the photons. We get a strong kick this way on the particle. And the weak one was A. Right? Strong kick, weak kick this way. So you see what happened? JB is bigger than JA. And which way is the net force? That way. So if the bead tries to move out of the beam, the impulse from the light pushes it back into the beam. And if I drew it over here, it would push it back into the beam. Right? So this is how you trap particles. Then if you focus it with a lens, it does the same thing this way. So all you do is focus light, and you have a three-dimensional trap for dielectric particles, and it's used in biophysics, and you win the Nobel Prize. The end. Okay, we'll see you Thursday.